Hello, everyone. So, my name is Chaim, who doesn't know me. So, today, actually, our tutorial will be starting of neural networks. So, today we will cover fundamentals of neural network mechanism, and we will deep into convolutional neural networks. And the next tutorial will be devoted only for for some advanced convolutional neural network and learning practice. So, actually, some revisited from a lecture. So, multi-layer perceptron is actually the way to solve nonlinear dependencies, unlike the single perceptron. So, actually, this the definition from the lecture. So. We actually combine perceptrons by that the input of the next layer will be the output of the previous layer, okay? And we have our non-linear function phi that actually a multiplier of each inputs, okay? Great. So, unlike to single layer contrapts, MLP have actually hypothesis that it starts from two layers and more, okay? And actually we can solve any degrees of input dependencies and and can actually solve any nonlinear functions, okay? So the number of for sufficiently large number of weights, because for a multi-layer perceptron we have for each outputs we have a connection from the inputs. Okay, so it's actually the PyTorch. Okay, so all our examples will be in PyTorch. In PyTorch framework, it's one of the common frameworks today, powered by Facebook, a small company. Okay, so actually, what we see here is declaration of linear layer. So we have first we need to define the number of features, input features, the number of output features. If we want biases, and actually this is the import that we should do for for defining our functions. So first it's import torch. It's actually that we have our torch in the Python framework. So and some functions that we will use in the few examples. So it's linear and ReLU. We will talk about it later. Some we can use actually NumPy and other Python packages as we wish. And torch autograd, it's our powerful function that derivate our variables. So first we will define my layer as linear function, okay? Then we will define some vector imp, okay? And then we can apply our linear function on our vector, okay? So let's see. Okay, so the output we have actually we have tensor. So this tensor is actually the solution of applicable of our it's we apply our input on our linear function and we have our output. So it's our y, okay?
What weights? What is the W in your example?
This is very good question, sorry. So you asked what weights. So weights is generated randomly, okay? Yeah.
Why we define my layer two times?
Can you speak loudly, please?
Why you define the layer two times?
Actually, I can define the. It's like I can define. It's a example of two layer perceptron. Okay. Okay, so actually I can define actually I can define that I can define it only once. Okay, it's it's only for example. Okay, again it's not a sequence. Okay, it's not a sequential neural network. It's only so it's only one thing. So okay, so now now my layer have a methods. Okay, so my layer have a methods. I can actually I can see my weights by actually method weight. Now I can see my weights this way. Okay, so here I have a tensor. Okay, and here I see my weights of my function. Okay, so okay. So here I have the weights is actually 10 in a row and 5 in columns. Okay, it's what I declared. Great, and here is biases. So what number of biases we expected here? 10 on 5. As number of inputs or outputs, what do you think? There are number of outputs. So if my the biases defines its number of outputs, tensors. So okay, so my weight, our weights, it's input feature in this size is input features on output features, and the biases is only one bias of each output feature. Okay, great. So we expect here, so we expected 5 biases. Great. Any questions? Again, you can ask a question. Any questions until now? No questions. Great. Why it's required? Okay, so where or why? Where I define it. Okay, again, okay. This is sorry. It's a good question. 1 minute. Okay, so actually, it's the default. Okay, actually, if I want to define a tensor that have no required grads, so I need to define it here, and I will mention require grads false. Okay, if I do not declare it, it's automatically by default require grads true. Okay, so it's actually tensors that we expect them to be trainable. Okay, great, very good. So here we have biases. So now we're starting to stacking the linear layers. Okay, so actually what we want to do, we want to build neural networks that have more than one linear layers. Okay, actually the neural networks that have more than one layers, it's called hidden layers. Okay, so more than one hidden layer, it's actually deep neural network. Okay, because one networks that have only one layer, it's actually shallow. So let's start to define deep neural networks. So here we have. Okay, so here we have actually. This is example of how we're stacking the linear layers. So we have my linear. It's a linear that have 10 input feature maps and 5 output feature maps, and the second one is my layer that have 5 input feature maps and 2 output feature maps. So what we actually do here, we applying my actually some input that we sent before on my layer, and have our my layer 2. Okay, it will be the input of my layer 2. Okay, yeah.
What is the function phi?
Which function?
The function phi. The nonlinear function.
Nonlinear. Phi. Okay, phi. Okay, yeah. So what you ask about?
You define two.
Yeah, this is example without nonlinear function. Yeah.
Both of your layers.
Both of my yeah. For now, it's both. Both of them have it's then actually linear layers. Yes, but actually, what we will do, in practice we will define some non-linearities between the layers. We will see more examples here today, okay, and not actually over the course. Okay, so for your question, so activation functions. Okay, so activation functions, actually the functions that make our neural network so powerful. Okay, it's actually activation function. So we can solve very sophisticated dependencies, okay, by applying activation functions. So today, actually, I will present you few of the common activation functions. In the next lecture, in the next tutorial, I will present you a few more, and etc. Okay. So today, actually, we will start from some common activation functions for actually that we used for MLP. So there are a lot of activation functions that actually used in neural networks. So sigmoid or tanh, okay. Actually, both these functions are more used in multi-layer perceptrons on convolutional on linear neural networks, okay, fully connected neural networks. Actually, they are heavy to computational. Okay, the guys who are dealing with hardware know what I'm talking about, and they're actually the very deep neural networks, convolutional deep neural networks, commonly not used in this activation functions. Okay, so the commonly used activation function for convolutional neural networks is ReLU. Okay, ReLU is actually a very simple function for each inputs that are bigger than 0. It's actually it will be the input itself, and from all the negative numbers, it will be 0. Okay. So actually, this function has its derivative of exactly 0 and for from minus infinity to 0, and exactly 1 from 0 to infinity. Okay. Justification why actually we use this function. Actually, there are no some strong justification, but empirically it gives a very good result. Okay, against the very small computational. Okay, so this is actually the reason. There are a lot of modification of this function. Okay, some of you maybe heard before some p-ReLU or some other functions that actually have some definition from their negative values. Okay. Actually, more some functions that are derived from the negative for the negative side, but actually, there are no clear justification to use this kind of function for a common convolutional neural networks. Okay, right, like ResNet or Inception or other common convolutional neural networks that actually are more are used today for solving classification, segmentation, and the other tasks, computer vision tasks. Okay. So, any questions? Great. You're so smart. Okay, so let's see some how we define activation functions in PyTorch. Okay, so here we actually it's our we have our torch tensor. Okay, so this here we mentioned that it's required grad 2. Okay. And we need to mention that our type is torch.float. Okay, so we need that our types will be float. Why do you think that the types need to be float? No, actually, why we expect that the types of the tensor will be float and not integer? Yes, because the gradients. Very good. Yes. because again we expect that actually if we will not define that the d type will be float or integer, actually we will have some warning or actually it's error that you cannot derive your function. Okay, yeah.
We're using specific float instead of the, let's say, default Python float to reduce bit representation?
This is good questions. Look, actually the default is using it's using 32 floating point representations. Okay, there are some reasons to use reduced representations like half float. Okay, it's fixed in float. Okay, it's some reduced float representations, but or even integer representation. But we will talk about it on some more. Yes. Actually, our course is deep learning for computational accelerators. So we will. I will talk with you on the lecture of compression, of quantization and compression, why we should to reduce the representations. Okay. For now, we use the common float representation. Okay.
Difference in calculating the gradient will not be significant. That means that
Yes. But okay, we will talk about it later because we have. Yes, you're right. When you use a small reduced representation, you have problem with your gradients and other problems. But we will solve them when in more advanced courses. Yes. Yes, sure. Actually, we have about the dimensions. So here we actually have some tensor. Okay, it's one the tensor with specific values. Okay. Actually, we will have tensor with four values. It's tensor 1/4. Okay.
so every time we use tensor, we need to give it 4 dimensions. It's a 4 dimensions vector. I mean, we define it by.
It's just one. It's not 4 dimension.
Yeah, I know, but we define it by 4.
No. You actually I could define it other way. Okay. It's an example. Okay, it's an example. You will see other examples with other dimensions. Okay, so here I will use. Okay, so let's continue. So here we apply our ReLU. Okay, our ReLU that I was actually imported it before. Okay, and for variable my ReLU, and now actually my ReLU it's. Applying it on sample data. Okay, so what the values that we expect to get? 1, 1 to 0 and 2 0. 1, 1 2 and 2 0. Okay, good. You was right. So actually we got the expected values. Yeah. From the function, for our function. Okay. Let's continue. Questions, guys? Yeah. I don't need requires grad for these operations. Actually, I declared some learned vector, but I couldn't. I can do it. This operation I can do on require grad false vector too. Yeah, it's you should not. It doesn't matter for applying real function if it's parameter. Only you cannot do require grads if you need. Yeah, for actually if you for applying rel you do not need to define tensor with required grads too. It's only an example. Great. So this is actually another way and more simple way to applying a rel function. It's by defining it from a functional from torch and .nn dot functional SF. Okay, so here we have all kinds of non-linearities and other functions. Okay, so here we actually define sample data. It's torch tensor, and we are applying it by f.relu. Okay, and sample data here f is actually contains our applying of non-linearities. It's more simple than do it this way by defining some function, some variable, okay. So we can use only existing variables. Any questions?
Yes.
Yes.
The tensor in the bottom is a capital T, and the tensor in the upper box is a lower T.
Yeah. So this is actually this tensor. Here we can define it. Okay. Here we can define if you want to require grad 2. This in this tensor is actually built in. Okay. You cannot you cannot you can use only some default initiations. Okay. I prefer. Okay, it's very good questions. Actually, I prefer to use this one. Okay. And because here you can you have you have the options to define by yourself. Okay, so neural network. So it's actually this is our first example of whole neural network. So we defined class, my first network. Okay, so it inherit the function nn module. Okay, so here we define it by the definite some some sequence. So we have self input size, hidden size, output size. Okay, so self dot layer 1, it will be an linear input size and hidden size, and self layer 2 will be some with some other okay, some hidden size output size. Okay, because we want actually from getting from here to here. Yeah, so we want to, if you have a classification problem, we want to have to feeding our input and to have our output size. Yes. So if our output is classes, actually if classes of some I don't know, some data that have 10 classes, so the input will be our pictures and the output will be 10 classes. Okay. So here we define by def forward. Here we define actually our how we do our feed forward of our neural network. Actually, our connections. Okay, because here is only definitions of our layers. Guys, it's a little bit louder here. Okay, and here, okay, we actually defined our connections. So we have our self, our input. So our out from it's actually will be self layer of our input. It will be our first output. And here we applying on non-linearity. Okay, so it's actually layer non-linearity and second layer non-linearity, and here our output. It's actually our targeted output. Okay, great. So loss functions. Yeah. Questions about the previous one? After here? No, actually after here we if it's I can do it, okay, but if it's function if it's a classification task, okay, so what I will apply it's softmax. It's actually inherit you have here there in inherit tan h, okay, so you do or sigmoid, so you do not you don't need to declare to define the input before softmax, okay. You do not need to define activation max before softmax. Okay. Okay. So loss functions. We will see more examples of with softmax. Okay, and then I will explain. Okay. So actually, when we talking about supervised learning, we have some finite sample of labeled of our labeling. Okay, we have X label, it's our input, and and Y is our output. So when we select some hypotheses that we want to minimize our function, our loss function, so actually the H star will be defined as argmin of all our losses, actually derivated summing on all our and not normalized for all our samples. Okay, then we actually in terms of learning, we want to minimize problems that can be written as theta star. Okay, so here we want to have argmin on all over our samples. Okay, and actually the loss defined like the loss of our theta, or actually learned parameter. It's defined like normalized on all over samples for each sample. Okay.
Missing in the loss function the label, not yi.
What?
You're missing in the
No. It's why? No. It's actually the y. It's here. Okay, it's actually combined here. Okay, it's a you are applying here and you get your yi. Okay.
then the point loss function needs to compare the output of the hypothesis to the
Yeah, sure.
actual,
Yes, and it's kind of your function, okay? Because you have a few kinds of loss functions. It depends, guys. It depends on your task, okay? So if your task is to predict some variable, okay? So it's actually a regression problem, okay? So there you have a few losses like L1 losses, and we will talk about it next tutorial, okay? So it's actually minimize the loss function minimize the function that you have your term, okay?
by the li.
Yes.
The fact that it's a
Yes.
li and not general L means that
Yes,
related
because
to the yi you expect.
yeah. It's actually expected that what I want to minimize. Okay, but in every cases of supervised learning, I want to minimize some term of target of my y tag y dot. Okay, some that I achieved by my neural network to labeled y. Okay, and this distance will be I want to minimize it. Okay. Yeah. So, okay. So here we define some loss function, though this is actually mean MSE loss function. So MSE is mean square error loss. Okay. It's actually mean square error loss is common used in regression problem when I want to make some approximation of when I want to approximate some function, okay, and I want to and my output it's continuous, is actually continuous one. So we will use by or MSE or L1 again all kinds of losses we will talk next tutorial. So here we have some input. So we have torch, rand. Here we have dimension 3, 3 and 5. Okay, three rows and 5 columns. So our target is actually will be again torch, rand, n. Actually, I have one question. Why in input I defined that requires that must be true, and the output I didn't define it. Actually, we want to approximate our output. Okay. Huh? Okay. So if we want, thank you, to approximate our function. Okay. So we have function y, and our function is actually some a w plus b. So actually, our y, it's our labeled. Okay, it's our label. I want to approximate it. I do not need I will not derivate my function in terms of y. Okay, I want to actually only derivate it by my in terms of my input. Okay, so I do not need to define my output as a required graph. Okay. So, great. So, we defined input, we defined target. Our output will be loss function of input and target, okay? So, that was I want to minimize, yes? And output that backward, it means actually that we have our back propagation, yes? Alex started to talk about back propagation. It's actually the process when we do our derivation in terms of our input and weights and calculate our new weights for the next iteration. Okay, so let's see what we got here. So in input, okay, great. So input dot grad give us all our gradients. Okay, so, yes.
Backward method is implemented superclass of the torch model.
Yes. Backward, it's implemented by superclass of torch model. Yes. Okay. So here we have tensor. Okay. So his dimensional, his the dimensions is actually 3 rows and 5 columns. Okay. It's actually it's the same dimension of our matrices of our inputs. Okay. Okay. So for each input we have gradient in terms of, okay, so and this is actually some it's initialized, it was initialized by some values and its derivation of it. Okay, so it is our gradients. Any questions? Yes.
The input are the features or the labels?
The features, of course.
Where are the labels?
I-
Can you compare to target?
No, I do not see that. Our actually, you're talking about our target
Target is the
labels. Yes,
okay.
the target it's my labels. Okay, so it could be numbers if it's regression, or it could be if it's classification. It's one hot that will be defined any of my classes. H. Can you repeat H function? Here. Again, H function it's example of some functions that you applied on input. Okay, it's the network. Okay, it's dependent. Yes, it's you don't see here. It's okay. It's our you need to see your old model. You don't see it here. Okay, you will see it in more advanced when we will define it on your network itself. Okay, it's actually what defined on your H is defined by your model. Okay, you do not see here model. Okay. No, it's actually in its term of input. It's not some. I'm not feed forward some neural network here. Yeah.
When you stated that the input is requiring gradients, does it automatically assign weights to each one of the input elements and then with some initial values and then the gradient is according to those weights?
Yes. Yes. Again, we can define we can choose some initialization to use. There are a lot of ways to initialize neural networks, and we will talk about it next tutorial. But here you have some inherent in initialization.
At the moment that I'm going to define something that's requiring gradients, it's going to get these weights automatically.
Yes, it will get your weights automatically. Okay? Yeah.
If I wanted to have the bias term, do it after the bias graph.
Again, if you want to add bias term, yes, if you want to add the biases, you need to define it here. This actually, guys, your attention, please. Thank you. So here, good questions. What's your name? Vital. Vitali, sorry. So Vitali asked, what about biases? So actually, this here we have no biases, okay? But we can define it here, okay? So we can define it by giving the operator of biases here. Yeah, more questions. Until now. If you have some questions.
You've done nothing on the network.
Yeah, I did nothing. Yeah. I have actually.
Random values and
Yeah.
calculate loss function.
Yeah. I will again. So here it's my old model. Okay. So here I have no model. It's only some. I only initialize its. Yes, it's a random result. Yes, but in the real example, we will in the real life of deep neural network, we have some deep model, and it's actually it's the applying of all model on my input. Okay, and this is actually will be my output, and I will derive it of expect in terms of this model. Okay, great. So. Some more examples of loss functions. So cross entropy, it's common. It's a common and only one function that actually we use for classification problem. Okay, so actually we have here true label and our predictions. Okay, if true label is 1, we return minus log prediction. Else we return minus log 1 minus prediction. It's actually function. It's loss function that we use for as loss function of for classification problem. Okay. Actually, Alex talked about it about softmax. Okay. So we have our log digits, so our vectors that we want to predict some classes. Okay. And here we calculate our loss in terms of our classes. Okay. So actually, again, is it clear? What is prediction here? Okay, what will be our true label? How it look like? Anyone else? He is from our lab, so he's biased. Yeah.
100?
Yeah, it's actually okay. So our true labels will be actually like it will be hot vectors that have 1 in the place of the specific class, okay, and 0 in the other ones, okay, because you can be, if you have data set, you can be only a dog or cat, okay. So in the place of dog it will be 1, and the other places will be 0, okay. And our predictions, it will be also this kind of one hot vector, and here we have our actually loss will be more smooth loss by using log, okay. Great. So, and some other example. So here actually you can use cross entropy loss from from PyTorch NN. Okay. So we define it here loss underscore fn. So we have the input output, and we have actually the same code than we've seen before. Any questions? And we have some gradients. Yeah. Questions up to now, guys? Yeah. Okay. Where is it? Long tensor. Third line. Okay. Actually, long tensor or tensor, it's declaration of tensor of tensor. Okay, it's only you have few declarations of tensors. Okay, that we have, and long tensors is one of them. Okay, actually it's commonly used. Okay, but you have actually we use it because it have a lot of methods before. You can use the randoms are the methods that you can apply it from long tensors. Okay, but it's actually tensors that have their type is 32 floating point. Okay, it's actually vectors. Yeah. Yeah.
The gradient here is only for the loss function. This is the only thing that you.
The gradient is
Yes, you calculate the gradient
yes.
only on the loss function, so you derive the derivative only on the loss.
No. You will see it in the next. You're asking me where I calculate my gradient.
Not where, but on what? What is gradient on?
In terms of loss functions. In terms of loss functions, you calculate it. It's on your inputs and your weights, okay, or your inputs outputs on your weights, okay. You don't see it here.
No, I don't see your layers. This is what bothers me. I don't see any layers.
No, because it's automatically when you declare your model, it's doing automatically, okay.
So you have here a neural network.
When I do my back propagation on my neural network, I calculate my gradients in terms of in respective to my inputs and my weights, okay, by minimizing my loss function, okay.
Talk about all the parameters as parameters for deriving the gradient, but the gradient function.
Yeah,
The loss function is the only function.
yes, we update. Okay. We update only weights. Okay, but calculation of the weights, of the calculation how we need to update it. It's made by both terms on my weights and on my actually input or outputs. Okay. Actually, we will define it. Okay. Okay, so gradient descent actually, or stochastic gradient descent, it's a common optimizer in neural networks. We will see few types of gradient descent that we will few of them will have only one parameter. The others will have a few parameters. Maybe a few of them will be learnable during the training, and a few of them will be fixed during the training. Actually, first we will start from some. It's actually vanilla gradient descent. It's a simple. It's a simple algorithm that works great. Okay, and find the local minimas. Actually, it's a common way to find local minimas in neural networks. Okay, so what let's go through the algorithm. So we are starting from some initial guess. Okay, select our step size. We will talk about the way how to define the step size smart. Okay, how we can define smart initiation of the step size. We update our weights in terms of gradient on loss. Okay, this is actually what you're asked. So it's gradient on loss multiple our step. Okay, and the next epoch step theta or parameter will be for the following. Okay, it's the previous parameter minus this derivation. Okay. It's actually how we update our parameters among our epochs, okay? Iterations. So when I talk about epochs, let's define epoch. It's like feed forward and backward, okay? So when I do one feed forward and one backward, it's one epoch, okay? It's one epoch on your network, okay?
On any sample, on every sample.
For any,
Forward on every sample.
yes, for every sample. I will do it for all all samples. It's when I finish my first doing the epoch for all samples of my data. It's the end of the first epoch. Any questions till now? No? Great. Very good. Oh, sorry. Okay. So here, Mhm. Oh, I did some mistake. Okay, great. So let's see. Okay, so here we have some functional. Okay, it's model sequential. So guys, a few minutes we'll finish. I think it's our will be our last slide, or maybe not. Let's see. So we define here model as NN sequential. So NN sequential, it's a common library for it's actually a common function for using for common class for defining few layers neural network. Okay, so here we have some NN linear. This is his actually input. Okay, and we have this is actually here 10 his output, and we have some softmax. Okay, so we will.
Defined one layer.
Yes, here I defined one layer, only one layer. Okay, so again, it's actually I defined it by this is the size of picture of some picture. Okay, and this is the output of number of classes. Okay, so it's actually the size of MNIST data set. Okay, we will see that that's it. It's that data set of digital of handwritten digits. Okay, so this is the number the input, and this is the output. Okay, so we have some bias here. We bias are true, and NN softmax. It's we applying NN softmax. It's the layer after my linear function. Okay. Great. So I have here data set. It's actually only it's some randomly inputs. Okay. So here it's actually inputs of it's one sample. It's one picture of 28 by 28. Okay. And here we have some random output. It's again it's the same sample. Okay, so our loss function is actually MSC loss. Okay, so here we have here we define our optimizer. Okay, so optimizer is our gradient descent. So it's optim dot HDD for model dot parameters. It's our parameters of model, what we want to optimize, and we defined learning rate as 0.01. Okay, for now it's some random initialization of learning rate. We will talk about how we define it smart later. Okay, so actually each step we have fixed step of our n here. Okay, and we each step we update our parameters by fixed step multiplied by gradients of loss function. Okay, great. So let's see some more example. No, I think okay. Next tutorial we will start with convolutional neural networks.